on that homework, because I had a couple people reach out to me today with questions on some of those problems. And usually I go on the assumption that if one person is asking a question, there's probably more than one person who has that question. And so is everybody all right if we start by looking at a couple of those homework problems? The first one was,
It says the homework's due the 21st, it says.
okay, then the 21st, and I had it written down wrong. Oh, you know what? I'm looking at the wrong chapter. Okay, let's do the 21st. Let me, before I mess that up again. Homework 3 is due 10/21. Now let's go back to that virtual textbook. Somebody asked me about question number 6, writing numbers in some of those other systems, and specifically the Babylonian system. Did you folks want to go over one or two of those? Anybody? Shall we? You guys are being quiet. Does anybody need help on any of those questions? Should we look at the 3022, changing that into Babylonian? Is everybody all right? Babylonian was a system where we had ones, and then we looked at numbers in blocks of 60s. And so that the next place value would be 60 to the second, which would be 3600. We had this symbol that meant 10, and it actually looked more like that, but I'm going to just draw a line to mean 1. And so if I want to take that number 3022 and write it into Babylonian. Is everybody all right? I don't need anything in the 3600 place value. It's too big. So I need to figure out how many 60s I need. So I'm going to take that number and think of dividing it by 60. Dividing it by 60 would give me 50 and a remainder of 22. So I need 50 groups of 60. 1, 2, 3, 4, 5. 5 tens would be 50. And then in the ones place, I need 22. And usually we leave a space in between there to show that there were no ones. How is that? The other questions that I got asked about dealt with that same idea, converting with units of 60, but instead of being in Babylonian, it was something that's much more practical, and it has to deal with the idea of time. And so this question over here, 22, in my mind is very similar to the Babylonian system, because in the Babylonian system, we moved over in groups of 60. And if I think about time, doesn't that work in groups of 60 in terms of minutes into hours? And so over here, question number 22, we're told that somebody works 6 hours, 35 minutes, 4 hours, 15 minutes, 7 hours, 30 minutes, 5 hours, 20 minutes. And we want to know how many 8-hour days, hours, and minutes this is equivalent to. So does it make sense? We'll start by adding the minutes. 5 plus 5 is 10. Then 1 and 3 is 4, 5, 6, 7, 8, 9, 10. That's 100 minutes. But now wait a minute. In terms of telling time, is there anybody who looks at a block of 100 minutes? What do you think we ought to do with those 100 minutes. Any ideas?
Would you make it an hour and 40 minutes?
Right. If it's over 60 minutes, remember it's down here, it says the number of minutes is less than 60, that's over 60 minutes. So I'm going to take that 100, I can think of dividing it by 60, which tells me I have 1 hour and 40 minutes. So I'm going to change this into 40 minutes and carry over 1 hour. Now I've got 10, 11, 18, and 5, 23 hours. But we're told that we're changing it into 8-hour days. And so it says to make sure the number of hours in our answer is less than 8. Well, if I take that 23 hours and divide it by 8-hour days, let's see, that'll go in there twice with a remainder of 7. So won't I break that down into 2 days, 7 hours, and 40 minutes? How's that look? Now, you guys look bored. I don't want to bore you, but I also don't want anybody to be confused on the homework before it's due. Does anybody have any questions at all from the homework that they need help setting up that they want to go over before we start looking at that new next chapter?
Would we be able to go over one more of them?
We can go over way more than one more. Honestly, in these long classes, usually for each class, the 3-hour class, normally it's 3 1-hour meetings. And I usually plan on at least 10 or 15 minutes of every class clearing up homework problems. So don't feel guilty asking about homework. I'm actually begging you guys to. I need to know where you stand. So what one do you want to look at?
We can, I'm trying to find the paper with them, but can we just look at another one? It doesn't matter which one. I'm kind of lost on all of them, so.
Hey, do me a favor and kind of dog ear the ones you're wondering about. If you want, we can take a couple minutes for everybody to rifle through what they've done so far on the homework. But I'm thinking the next one that somebody had asked me about was on page, I think it was 144, I'm thinking. And I'm thinking it was question number 7. So I have to move you guys. And this one, again, is real similar to the one that we looked at with the Babylonian numbers, pardon me, and with the time. It asks us to do addition and subtraction with time. And so that first one, we've got 3 hours, 24 minutes, 54 seconds. And we want to add to that 2 hours, 47 minutes, and 38 seconds. And again, we're all familiar. How many seconds make a minute?
60.
How many minutes make an hour? 60. So we want to make sure that we never want to have more than 59 seconds or 59 minutes in our answer. So here when I add, I'm going to start adding with the seconds. 4 plus 8 is 2, carry the 1, 6 and 3 is 9. Oh my heavens, that's 92 seconds. That's over a minute, isn't it? So what do we have to do? we have to take away 60 minutes. And when I take away 60 minutes, I'm sorry, we take away 60 seconds. When I take away 60 seconds, doesn't that become a minute? And I'd be left with 32 seconds. Now let me add my minutes. 1 and 4 is 5, plus 7 is 12. And then 3 and 4 is 72. Oh dear. Should I have 72 minutes? No, we're going to have to take away 60. So that'll leave me with 12 minutes, and it adds an hour. And so this adds to 6 hours, 12 minutes, and 32 seconds. And isn't that like the exchanges but with a different base? We're working with a base of 60. Gets a little dicier when we subtract. If I look at C, we've got 5 hours, 24 minutes, 54 seconds. And I want to take away 2 hours, 47 minutes, 38 seconds. First, I'll subtract the seconds, and we can take 38 away from 54. Let's see. Bring down my S for seconds. That's 16 seconds, and life is good. But now, wait a minute. Can I take 47 away from 24? No. So I'm going to have to do an exchange. So over here, this will become 4 hours. But when I add an hour, how many minutes am I really adding in? 1 hour is how many minutes?
60.
60. So doesn't that turn this into 84 minutes? And so now when I subtract 47 from 84, let's see, I'm going to have to do a little bit of borrowing. That gives me 37 minutes. And now I can subtract the hours. That any better?
Yes.
All right. Any other questions that anybody wants to look at? To me, they're all fun. And so I don't mind going over them. Was there any place else in this homework that's due in a couple days that anybody had difficulties that they want to go over? And again, please ask. Don't be embarrassed to ask, because my guess is if one of you had a question on a problem, more than one of you had a question on a problem. And so you're helping out the class. And I'm not a mind reader, so I'm not real sure on which ones you might need a little guidance on. So help me out, folks. Does anybody want to look at any others? How did everybody do on page 153? There was one question in there that, how's everybody doing on page 153? There was a little bit different than what we did in class, but I assign it because through my years of teaching at the college, I know people who multiply this way. And so because I've had students that multiply this way, I thought, well, it's different than any of the models that the authors presented. It's an interesting one. How did you folks do with the question on page 153, question number 17? Multiplying using that lattice method. And then the very last page of the homework, how did you folks do with the different bases? Wow, this is slow. Was it fun drawing the blocks, math, sticks, and units? If we were in class, we'd spend time handing out the manipulatives and doing that. Why is this not turning pages for me? How did you folks do with the multiplication using the lattice method? Is that something that you have seen before or no?
No.
No. Did anybody want to go over a problem like that together?
Yes, please.
Okay. Rather than doing the ones that they told us to do you want to give me 2 3-digit numbers that you want to multiply? How about
612.
612? And what do we want to multiply that by?
36.
36. So when I take 6 times 2, I get 12. And I'm going to write my 2-digit numbers like that. When I take 6 times 1, I get 6. When I take 6 times 6, I get 36. With me so far? Now, when I take 3 times 2, I get 6. So I'll write that as 0, 6. 3 times 1 is 3. And 3 times 6 is 18. And now I'm going to add along the diagonal. So here along this diagonal, I have 2. Along this diagonal, 6 plus 1 is 7 plus 6 is 13. So I'll put down the 3 and carry the 1. Along this diagonal, I have 4 and 6, which is 10. Along this diagonal, let's see, 9 and 3 is 12 and 6 is 18. And then along the last diagonal, I'll have 5. So 612 times 36. Oh no, wait a minute, you guys, this 6 and this 3 haven't been added in. I knew that looked wrong. Sorry about that. 9 and 3 is 12, carry the 1, 1 and 1 is 2. I'm sorry, that 36 shouldn't have been part of my diagonals that I was adding. That product gives me 22,032. And if you stop and think about the more traditional way of multiplying those numbers, I would take 6 times 2 is 12, carry the 1, 6 times 6 times 1 is 6, plus 1 is 7. 6 times 6 is 36. And then when I multiply the 3, because I'm multiplying by the 30, I move over. So moving over place value is like putting it in the different diagonal on the lattice. 3 times 1 is 3. 3 times 6 is 18. And so when we add down, oh, Lord, help me. It's one of those days. I get that same answer. And so just putting them in the diagonal places in that box on the lattice is like keeping track of those place values. Have any of you seen multi-digit multiplication like this with this lattice method? Yeah, I've surprised the number of students that I've seen through the years that use that for multi-digit multiplication. So, all right. Any others anybody wants to look at. How's everybody doing with that last page of the homework where you're changing bases? Is that something that you're all comfortable with or no? Silence. All right, can I go on the assumption that if nobody's saying anything, life is good? I can only see
Yeah.
some of you. Yeah, we're good? Okay. If you still have questions on the homework, please email me or stop by my office hour tomorrow morning, although tomorrow morning I do have a couple of advisees stopping in. Okay, then next, and I'm rethinking. We're supposed to be having that second test at some point in time during the course of this week. I was thinking, let's see, and I'm open to suggestions here, I guess. Homework 2 is due the 21st, which is Wednesday. Right now, I have the test in Blackboard, and I have it open from tomorrow morning till Friday evening. Is it Friday? What day is the 26th?
Monday.
To the Monday. I'm just wondering if having it open on the 20th is premature. You might want to, if you want to get started, then you can. You might want to wait to start it until after your homework is graded. And I will try to grade them if they're due by the end of the day Wednesday. I'll make sure that they're all graded by the end of the day Thursday. For that test, you have 75 minutes. Each of the questions, there are 13 questions. Each of the questions has a place where you can type in your answer in essay format. But I know some of it, it's easier to just write it out than type it out. And some of them you have to draw for. And I didn't want to put a separate drop box for you to enter pictures in each question because I think that would take too much time. And so during the timed test, I want you to just do the questions. And if you want to, instead of typing explanations, want to type something handwritten or show work or show a diagram, just tell me that in the essay part of the question and submit the picture in the drop box. So that if I look right now in Blackboard for this test, you're going to see that I made a separate folder for the test. Exam 2 is on chapters 2 and 3. And the first part is the exam itself. You only get one attempt, so don't click on it and then close it because you're done. You only get one attempt. You have 75 minutes. If you can't, type your explanations, if you're doing it pencil and paper, just again, in the essay place, type me, look at the other drop box. And over here, you can have that drop box to submit the pictures of the work. All right. Did anybody want me to walk you through what type of questions are on that test?
Yes, please.
Okay, it has 13 questions. Again, they're essay where you can type things in, or you can use the Dropbox to submit pictures. There are 2 questions that ask you to change base. One asks you to go from a different base into base 10. One asks you to go from base 10 into another base. There's a question where you have to draw the blocks, sticks, and units. and show exchanges. That one you have to draw. There's a long division that you need to do by the scaffolding method. There are 2 questions that deal with ancient number systems. I'm not asking you to memorize the symbols for things like the Egyptian and the Babylonian and the Mayan. I am asking you to know the symbols for the Roman numbers, because Roman numbers are used commonly in today's culture. There's a question where you have to do a couple of different operations showing them on a number line. In terms of showing them on a number line, I had a little bit of issue when people did their number line operations on the homework. And so I should clarify that before you get tested on it. If I ask you to show on a number line, let's start with 5 plus 4. When you draw your number line, you want to start at 0. You're going to have a single arrow that goes from 0 to 5. And you have to put the arrowhead on to show that we're going from left to right. And then from here, we're going to have a single arrow with a length of 4. And so 5 plus 4 takes me to 9. Instead, if I asked you to show on a number line something like 8 minus 6, I'm starting with a number line that goes from 0 to 8. And then remember, when we subtract, we're going to draw another arrow backwards. It'll have a length of 6, 1, 2, 3, 4, 5, 6. But the arrowhead should also be pointing to 8. And so we'll say that that difference is 2. And it's kind of based on that missing addend definition of subtraction, where did I need to start from with that arrow of length 6 to end at 8. So when you draw your number lines, make sure you put those arrowheads on the end of each. Then there's some set questions. You're given a set and you're asked to, on that set, do complement, union, intersection with a group of sets. There's some set notation where you're asked to read set builder notation, write set builder notation, describe a set, all those different ways of showing a set. And then there's some set questions, not as involved as the ones that were in the homework, but where you have to draw a Venn diagram and shade in the regions that are represented by the operation. Did you folks want to see an example like one of those from that homework, that last homework? Because that was one place that where some people weren't real strong. Let me see.
Yes, please.
I am trying to find. Let's look at, for example, if I ask you to shade, and give me just a minute. I think the ones that were on the homework were a little bit more involved than what I put in the test. Let's look at, I don't know. Let's look at D, which was A complement, union, B intersect C. Make sure when you draw a Venn diagram, you label what A, B, and C are. Inside the parentheses, the first thing that I want is B intersect C. Intersection is like where the streets cross, where the sets cross. And so B intersect C is this part. Now over here, A complement is everything outside of A. And so everything outside of A, if I think of going around this circle, I want everything that's outside of A. And then here, when I'm taking the union of those two, I'm combining them. So when I combine everything outside of A with where B overlaps C, this picture's getting messy, so I'm going to try to use a highlighter. It's going to be everything outside of A combined with the overlap of B and C. And yes, I failed coloring in elementary school, but you get the idea with the union is combining the two. Should we try another one? Next, let's look at, Lord. A union, this was B. A union B intersects C complement. So first I want to say, where does the inside of B intersect outside of C? Inside of B would be this part. Outside of C would be everything not in C. And when I look for the overlap of the inside of B with the outside of C, isn't that what those two regions would have in common? Now I want to union or add to that everything inside of A. And so I have A combined with what's inside of B and outside of C. Does that make any sense, folks? So in addition to the Venn diagrams, there is a question that asks you to, and this is a question that I took from the textbook, compare the ideas of equal and equivalent with sets. And then there's a question that asks you to work with exponential, work with the laws of exponents. The law of exponents question is rather similar to the one that was on the homework that I just graded and in theory gave back. So that covers the 13 questions that are on the test. Does anybody have a question about any of that on the test stuff?
When is the test again?
It will be available at 1 o'clock in the morning tomorrow, and it will be available until midnight on the 26th.
Okay. We gotta do this on our own.
You're doing it on your own.
Okay.
You have 75 minutes, so an hour and 15 minutes to complete the 13 questions. Don't submit your pictures until after you've submitted the test, because I don't want you to use up that 75 minutes worrying about the technology side of things. But I expect the pictures to be submitted soon after the test is finished. And yeah.
Okay.
Okay. So everybody all right with what's going to be on that test? And nobody has any more questions on that homework that is due in 2 days. Nobody wants to look at any more of those. If not, oops, I got to start sharing my screen before I go back there. Sorry about that. If not, I want to skip this prime and composite thing for a minute and look at in chapter 4 notes, really teeny tiny bit of the beginning of, oh, wait, back, go backwards, hello. This homework is due November 4th. And on that very last page, page 212, question number 7, only do parts A and B. There's no need for you to go further. Tiny bit of introduction, page 2. This chapter looks at the study of numbers. And when we talk about the study of numbers, we're referring to the idea of number theory. And I do want to go in and fill in that chart that I had on the first page, but it looks much prettier the way they present it in activity 4.1. And so I took the liberty of, at the end of the notes, uploading that activity 4.1. And so it says, we want to develop the concepts of prime, composite, and square numbers using a geometric model. And so in the back of your activity manual, there's a pouch of little squares, or you can look at centimeter graph paper. It says you're supposed to work in groups of 3 or 4, but I guess we'll just work in a big group altogether. You're supposed to either use the squares or graph paper to form all of the different rectangular arrays that you can make with each of the different numbers of squares. And you're supposed to record your results in the table. So, for example, if I only had one square, is everybody all right? With one square, there's only one way of doing it, right? It would be a 1 by 1 rectangle, and there's only one. If I had 2 squares, couldn't I make 2 different rectangles? This kind of short, fat one, which is 1 by 2, or this kind of tall, skinny one, which is 2 by 1. And so how many rectangles do I have? 2. In the same way, if I had a rectangle that used 3 squares, I could have 1 by 3 or 3 by 1. So there's 2 possible rectangles. Could you folks play around drawing on the side and see if I have 4 squares, how many different rectangles I can make and what their dimensions are? And the same with 5. They did 6 for us. So let's see, 6 could be 1 by 6 or 6 by 1, 3 by 2 or 2 by 3. So there's 4 different ones. And could you go through, please, and look at the remaining? I'll give you, what do you think, about 5 minutes to draw those out on your own? Do you think 5 minutes is enough time?
Are we drawing the actual rectangles?
Unless you can think of another way of getting them without drawing them.
Okay.
So how is everybody doing? Are we close to filling in this table or not quite yet? Do we need another minute? Are we at that go over place or not? How many rectangles did you get with, did everybody get 3 rectangles with 4 blocks, 2 rectangles with 5 blocks? How many rectangles did you get with 7 blocks? Anybody? I've got 1 by 7, and then I could turn that on its end. But I think if I looked for any other dimensions, I'd have extra blocks. It wouldn't be even. So that's 1 by 7 and 7 by 1. How did you folks do with 8 blocks? How many rectangles did you get? Do I have to start bribing you guys with extra credit or something to make you talk? Anybody?
I was still working on it.
Okay, then we wait. I think that was the first question I asked. Are you ready to go over or not? Nobody said anything. We'll give you another couple minutes. Go ahead. Tell me when you're ready.
I think I got it.
Okay. How about everybody else?
I think I got it too.
Okay. So how many rectangles did you get with 8 blocks?
I think I got 3.
3? What were the 3 that you got?
I got 3 too.
1 times 8,
1 by 8,
4 times 2,
4 by 2,
and then 8 by 1.
8 by 1. Now I want to take a minute and look at that 4 by 2. It looks something sort of like that.
Yep.
Could we have put it
A different way.
end and gotten 2 by 4?
Yep.
So I think we're going to add one more, which is 2 by 4,
4. Yep, we have 4 altogether.
which gives us 4 altogether. Does that make sense?
Yep.
Okay. All right. And I have to apologize. When I say 2 by 4, does anybody else think of lumber? Never mind. So how about 9?
Oh,
I think the obvious is 1 by 9,
1
Yes.
by 9 and 9 by 1.
9 by 1. Is there any other square that I could, rectangle, pardon me, that I could make with 9 squares?
3 times 3?
I got 3.
3 times 3. And reversing wouldn't make a difference with that one, would it?
Nope.
So this time we've got 3 of them, huh?
Mhm.
How about 10? The
1 by-
obvious is 1 by 10. Then we've got 10 by 1. Anything else?
5 by 5.
5 by, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm thinking if I've only got 10 blocks, wouldn't that be 5 by 2?
Oh yeah, 5 by 2, my bad.
And then can we turn it?
Yep,
So 2 by
2
5.
by 5. Mm-hmm.
And so that gives us 4. How about 11?
Two.
Yeah, isn't there just 2, the 1 by 11 and the 11 by 1?
Yep.
Okay. Now, how about 12? Let's see, it could be 1 by 12. I'll do the hard one. 12 by 1. How else can we break up 12 blocks?
6 by 2.
6 times 2.
6 by 2. And then we could go the other way, right?
2
2
by
by
6.
6. Anything else?
4 by 3.
4 by 3. Any other, and then we could reverse that, right? 3 by 4. So what do we have? 1, 2, 3, 4, 5, 6. Does anybody see any more, or does that look like it's
2, yeah, because it was 6.
so what's with all of this block stuff anyways?
Is that how they measure lumber?
Then usually the lumber comes like by like 2 by 4 or 4 by 4, you know, by the dimensions. But it's weird because it's not exact. It's kind of like smaller. And so like an inch is almost more like 3/4 of an inch, 7/8 of an inch or something like that. It's weird. Have you guys ever worked with lumber?
My fiance did. He used to do it. He used
At
to work
what-
at a lumber place.
Okay. At one point in time, one summer when all of my kids were working and my husband was working and I was home alone, I took on this project and I built a picnic table and bought so much lumber. Oh my heavens. And it lasted for a while, but I bought cheap wood and the bugs ate it. So let's look at the results from table 1 to complete table 2. So how many squares produced only one way of doing it? I think it was just the number 1, right?
Yep.
Which ones produced 2 ways of doing it?
2, 3, 5, 7,
Um,
11.
and 11. 2, 3, 5, 7, and 11. So more than 2 arrays. I guess they would have to be the rest of them, right? Which would be 4, 6, 8,
8, 9,
9,
10, and 12.
and 12. Now, which ones had an odd number of ways of doing it?
4 and 9.
4 and
Sure.
9, right?
Mhm.
Suppose you had 24 squares. How many different rectangles could we make with 24? Let's see. 1 by 24. 24 by 1. What else? Any
8 by
guesses?
3. 8 by 3.
8 by 3. And then 3 by 8.
Mm-hmm.
6 times 4.
6 times 4. So 4 times 6. How about 2?
Mm-hmm.
2 by 12. 12 by 2. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. So which column would it go in? A, B, C, or D?
C.
D. Now, what are the factors of 24? What numbers go into 24 evenly? 1, 2,
2, 4.
3,
Oh, 3, 4, 6,
6,
8.
8, 12, and 24.
Mm-hmm.
2, 3, 4, 5, 6, 7, 8. There's 8 factors of 24, and there were 8 arrays. Let's go back here. Isn't there only one factor of 1?
Mm-hmm.
And there was only one rectangle. How many factors does 2 have? 2, just 1 and 2, and there are 2 rectangles. And do you notice that the number of rectangles is equal to the number of factors that we have? So, okay, what are the possible factors of 16? What numbers go into 16 evenly?
2,
Okay, can we do one first though? 1, 2,
1, 2, 4,
8.
6. Oh, 16. Duh.
16. And so how many rectangles do you think we could make if there are 5 factors?
5.
5. And what columns would that be in? C
C.
and D, right? Because it's an odd number. So how is the number of factors related to the number of rectangles? They're the same, right?
Mhm.
The number of rectangles equals the number of factors. Begins with an F, by the way. So why is it that the numbers in column D produce an odd number of arrays? Let's see, D was the 4, the 9, and we said 16 would also fit in D, right? What do all of them have in common, the ones that have an odd number of arrays? What does the number 4, the number 9, and the number 16 have in common? Any ideas?
Can you repeat what you just said?
What they're saying, the numbers in column D, what do they all have in common? What does the number 4, the number 9, and the number 16 all have in common? Which way?
All square roots, I think.
They're all squares, right? There are perfect squares. Right? It's 2 squared, 3 squared, 4 squared. So what would be the next 3 numbers that would be in column D?
25, 36, and 49.
25, 36, and 49. Great. And so what's the mathematical name for the numbers in column B? The ones that only have 2 arrays, the only ones that only have 2 factors. If we look back here, the ones that can only be written as 1 times itself. Does anybody know the name for that type of number?
Prime.
Prime. Now the ones in column C had more than 2 arrays. They had more than 2 numbers that went into them. Does anybody know the fancy pants name for a number that has more factors than 1 in itself? Has anybody heard of composite numbers? And then column D would be our squares. And at that point, are you guys all right if we leave off the activity and start filling in this information in the notes packet? Was it a little bit more interesting coming up with some of these by making rectangles? I hope so.
I feel like I like the activities before we start the notes because it actually helps a lot more.
Good.
After.
Actually, at one point in time, I tried to flip this class and tried to just do activities and homework problems in class and have everybody do the reading and listen to the lectures on their own. Because if you read any of the literature that the authors of the textbook put together, in their minds, there should be no lecture in this class. In their minds, this class should all be activity-based, and from doing the activities, you should be able to come up with everything to do the homework. But when I tried it, it didn't work that well. So I'm, trying to do a mix of both. It's with the virtualness of the class, it's a little bit more difficult doing activities, but I'll try to squeeze more in, okay? So number theory is the study of numbers. One thing that an older edition of the textbook talked a lot about, that this one doesn't, but I feel it's worth mentioning. Has anybody ever heard of a perfect number? A perfect number is a number that's equal to the sum of its divisors, excluding itself. And there aren't very many of them. I think, and I have to apologize, I don't remember which mathematician it was attributed to, but someone was attributed to quote, perfect numbers, like perfect men, are very hard to find. And so one example of a perfect number is the number 6. If I look at the number 6, what numbers go into 6 evenly?
2.
1, 2, 3.
Mm-hmm.
And so those are the factors. And isn't 6 equal to 1 plus 2 plus 3? And then the next perfect number is 28. What numbers divide 28 evenly? 1. What else? Does 2 go into 28? Anybody else think of another number that goes into 28 evenly?
Four.
4. Now, how many times does 4 go into 28?
7.
7. And how many times does 2 go into 28?
14.
14. And if I take 1 plus 2 plus 4 plus 7 plus 14, what do they add to?
28.
28. And so that makes 28 the perfect number. And those are sort of interesting. In our study of number theory that we're going to be looking at, we're going to spend a lot of time looking at divisibility. And so technical definition, we're going to say that if A and B are whole numbers, where B does not equal 0, and there exists another whole number Q such that A is equal to B times Q, we can say, and there's all sorts of different wordings. We can say that B divides A. We can say that B is the factor of A. We can say that A is divisible by B. We can say that A is a multiple of B. And so does that make sense that if A can be thought of as B times some other number, that means that B would divide A evenly. B is a factor of A. A can be divided by B. And also A is a multiple of B. So far, so good. And that gets us into some of those terms that we just looked at with the activity. Prime number. How can anybody define for me the idea of what a prime number is? See, when we looked at the table, the prime numbers were the ones that only had two rectangles or two factors. So a prime number is a number that's only divisible by one in itself. It has two factors. And so from the table, let's see, 2 was a prime number. 3 was a prime number. Can anybody remember any other prime numbers?
5,
5, beautiful. Any others?
11.
11, great. And so those would all be examples of prime numbers. A composite number is a number that has more than two factors. And so if we think back to that table that we just made, I think one example would be 4. Can anybody think of another number that had more than two factors?
Is there 6?
Yep, 6. Not 7. How about 8?
Yep.
Yep. And the list could go on and on and on. And so we're going to be spending a little bit of time looking at prime numbers and composite numbers. So then the question comes up with, what's 1? 1 is neither prime nor composite. One is considered the basic unit. Because 1 has only one factor. And so following along with the textbook, once they go through and look at these definitions, they talk a little bit about representations, and I mean algebraic representations of even numbers and odd numbers. So what is an even number? Any ideas? You've heard of even numbers. 2, 4, 6, 8, 10. What do they all have in common?
Multiples of 2.
They're multiples of 2. And so could I say that they're represented by 2 times some value k, where k is a whole number? And so odd numbers, the opposite would be not multiples of 2. And has anybody ever seen an algebraic representation of odds? Evens are 2 times some number k. Anybody have a conjecture about what we would have to do in order to get an odd number? See, my evens are 2, 4, 6, 8. My odds would be 3, 5, 7, 9. What's the relationship between an even number and an odd number? Any ideas? Let's see, my evens are 0, 2, 4, 6, 8. My odds are 1, 3, 5, 7, 9. What's the relationship between the even numbers and the corresponding odd numbers? Does anybody see anything?
They add by 2.
They're okay, going this way they add by 2, but if I compare this way, if I compare each even to an odd, aren't the odd numbers 1 more than the even numbers? And so the way we represent odd numbers is 2k plus 1. 1 more than an even number is odd. And so again, k is a whole number. Which is sort of interesting. Any questions so far? If not, I'm going to go on to the next page. And I'm looking at the way I outlined the notes. I want to start in the middle with something that's called the fundamental theorem of arithmetic. And it says that every number greater than 1 can be expressed as a product of primes in one and only one way. Excluding order. So every number bigger than 1 can be expressed as the product of primes in a unique way. The only way we can get different representations is if we change the order, but those prime factors would always be the same. And so now I felt it's important to kind of clarify that before we go to the top of the page and look at the prime factorization of a number, or ways of writing it as the product of primes. And one way of writing a number as a product of primes is with a factor tree. So let me look at the number 420. In order to come up with a factor tree, I want to have any two numbers that multiply to 420. Is there anybody else in the room that when you see a number that ends with 0, you know it can be divided by 10? And so that would be 10 times what?
I can learn.
42? Now, how about the number 10? Can anybody think of any numbers that multiply to 10?
2 and 5.
2 and 5. Are there any numbers that multiply to 2, or is it prime?
It's prime.
How about 5?
It's prime.
It's prime. Now, how about 42? Are there any numbers that multiply to 42?
6 and 7.
6 and 7. How about 6? Are there any numbers that multiply to 6?
3 and 2.
3 and 2. How about 7? Are there any numbers that multiply to 7? Or is it prime?
Prime.
Prime. How about 3?
It's prime.
Prime. How about 2?
Prime.
Prime. And so the prime factors would be 2 times 5 times 3 times 2 times 7. And they're all prime. Have you folks done factor trees previously in your mathematical career? Is that something you've seen before?
Yes.
Right. Another way of getting those factors is with something that's called short division. I'm going to start with that same number, 420, and I'm going to try to divide it by the smallest prime number, or 2. Does 2 go into 420? 2 goes into 4 twice. 2 goes into 2 once, and I'd have a 0. Is that still even? 210? So now I'm going to divide that by 2 again. How many times does 2 go into 210? 2 into 2 once. 2 doesn't go into 1, but 2 goes into 10 5 times. It's no longer even, so I'm not going to try to divide by 2. But let's see, can I divide 105 by 3? 3 goes into 10 3 times, which would be 9. So I'd have 15 left over. giving me 35. 3 doesn't go into 35. So the next prime number I'm going to try is 5. 5 goes into 35 7 times. And now 7's prime. And so 240 gives us 2 times 2 times 3 times 5 times 7. And do you notice both ways I get the same factor? The only difference is the order in which I wrote them. And then once I have that prime factorization, we can look at it as a prime power factorization. Rather than writing that 2 twice, I could say it's 2 to the second times 3 times 5 times 7. And so I'm going to ask, could you folks please, either doing a factor tree or short division, find the prime factorization and the prime power factorization of, let's look at 180. And again, it's up to you whether you use a tree or that short division. One method or another, could you give me the factorization of 180?
Quick question. Do we have to do both of, do we have to do the short division too?
No, one or the other, whichever one makes you happier.
Okay.
Okay. Did anybody get a prime factorization of 180 yet, or is it still a work in progress? Do you want me to wait a minute? Let me know when you're done.
I got 2 times 2 times 5 times 3 times 3.
So that would be 2 to the second times 3 to the second times 5.
Yes.
All right. Now here's the question, the $6 million question. Did everybody else get the same?
Yes.
Yes.
So we've got that unique prime factorization. And so once we've got that unique prime factorization, I'm going to change this next example a little bit. Rather than listing all of the divisors of 180, let's list all the divisors of 420, all of the numbers that go into 420 evenly. And in order to do that, let's make an ordered list. Using our factorization. And again, our factorization of 420 was 2 to the second times 3 times 5 times 7. So first, I'm going to write those factors, 2, 3, 5, 7. And first, I'm going to look at each of them having an exponent of 0, which would give me 1. Then I could look at 2 to the first times 3 to the 0 times 5 to the 0 times 7 to the 0, which would give me 2. Then I could look at 2 to the second times 3 to the 0 times 5 to the 0 times 7 to the 0, which would give me 4. Then I could look at 2 to the 0 times 3 to the 1 times 5 to the 0 times 7 to the 0, which would give me 3. 2 to the first, 3 to the first would give me 6. 2 to the second, 3 to the first would give me 12. Then I could get 2 to the 0, 3 to the 0, 5 to the 1, 7 to the 0, 2 to the 1, 3 to the 0, 5 to the 1, 7 to the 0, 2 to the 1, 2 to the 2, 3 to the 0, 5 to the 1, 7 to the 0 would be 7 times 5 or 20. Then we could do the same with everything to the 0 power except 7. Then I could take the 2 times the 7 to get 14. Then I could take the 2 to the second or the 4 times the 7 to get 28. Then I could take, let's see, the 2 to the 0, 3 to the 1, 5 to the 1, 7 to the 0. And we could continue this pattern, right? That would give us 15. Then 2 to the 1, 3 to the 1, 5 to the 1 would be 30. 2 to the 2, 3 to the 1, 5 to the 1 would give me 60. And we could carry on like this, couldn't we, to get that entire list? Let's see. We could do 2 to the 0, 3 to the 0, 5 to the 1, 7 to the 1 would be 35. 2 to the 1, 3 to the 0, 5 to the 1, 7 to the 1 would give me 70. 2 to the second, 3 to the 0, 5 to the 1, 7 to the 1 would give me 140. Then we could have the 3s and the 7s, 2 to the 0, 3 to the 1, 5 to the 0, 7 to the 1. 2 to the first, 3 to the 1, 5 to the 0, 7 to the 1 would be 42. 2 to the second, 3 to the 1, 5 to the 0, 7 to the 1. Let's see, that would be 21 times 4, which is 84. We've got the 3 with the 7, the 5 with the 7, the 3 with the 5. I think what we still need is 2 to the 0, 3 to the 1, 5 to the 1, 7 to the 1, which would be 35 times 3 is 105. 2 to the 1, 3 to the 1, 5 to the 1, 7 to the 1, be 210. 2 to the second, 3 to the 1, 5 to the 1, 7 to the 1 would be 420. And oh my heavens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There's 24 divisors. Did I miss any? Does that look like about it? Maybe, just maybe, we should try to come up with a way of counting how many divisors a number has. Because does anybody else, when you make a list like this, don't you feel better if you know how many things are supposed to be on the list before you start it? So and is everybody comfortable with how I made this list? Because you guys are being really quiet again. And when I get silence from you, I get scared. Is this all right? Or am I speaking a foreign language? Hearing no complaints then?
I think someone commented in the chat box.
Oh, did they? Oh, okay, thank you. Yeah, it's okay. All right, then let's move the chat box down here so I'm sure to see it. And I have to cheat. I cut and paste this from the virtual textbook. Theorem says the divisors of a natural number. Let n be a natural number whose prime power factorization has the form n equals p to the a, q to the b, b to the c, for p, q up to b are raised to the powers a, b, c. A number m is a divisor of n if and only if m has a prime factorization of the form m equals p to the j, q to the k, b to the, well, I can't even see what that one is, where j is between 0 and a, k is between 0 and b, c is between, l is between 0 and c. And the number of divisors is a plus 1, b plus 1, c plus 1, and take the product. Holy crap, what's all that mean? If I go back to this first part, when I tried to show all of the divisors of 420, I looked at its prime factorization. And I said, okay, if it's going to be a divisor of 420, it's got to be powers of 2, 3, 5, and 7. And then I substituted in whole number exponents until I got up to the exponent on the divisor, on the prime factorization, but I can't go higher than that. And so the highest power on 2 is 2. The highest power on 3 is 1. The highest power on 5 is 1. The highest power on 7 is 1. And I have to take all of the numbers from 0 up until those exponents to get those divisors. And now the second part of the rule says, well, if I've got 420 is equal to 2 to the second times 3 to the first times 5 to the first times 7 to the first, I'm going to take each of those exponents and add 1 to them. So that gives me 3 times 2 times 2 times 2, which gave me 6, 12, 24 divisors. So let's look at the same idea again, but with a smaller number this time. Let's look at 60. if I look for the prime factorization of 60, can everybody take a minute, please, and make me that either the factor tree or the short division to get me the prime factors of 60? What are you folks getting for that factorization of 60?
I got 2 times 2 times 3 times 5.
So can I write that as 2 to the second times 3 times 5? And so writing it that way, if I want to know the number of divisors of 60, let's see, that 3 has an exponent of 1, that 5 has an exponent of 1. So I'm going to add 1 to each of the exponents. 2 plus 1 is 3. 1 plus 1 is 2. 1 plus 1 is 2. And so that tells me that I should have 12 divisors. Is everybody all right with where the 3 times 2 times 2 came from? And so that tells me when I make that list of divisors, I should come up with 12 of them. So now if I want to list the divisors of 60, do you folks want to use the factorization to list those divisors? Or do you want to just start listing off numbers that go into 60 evenly? I'll leave it up to you. Anybody have a preference as to which method we use? The authors like that method of going through and looking at the exponents, but not gonna lie, I kind of like starting with, well, that's 1 times 60. Does 2 go into 60? How many times?
30.
30. Does 3 go into 60? How many times?
20.
Does 4 go into 60?
15 times.
15 times. Does 5 go into 60? $12 times? Does 6 go into 60? How many
10
times? 10 times. And let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here we've got all 12 divisors. And so I think sometimes knowing how many you have helps you list all of them because you know when you can stop. Does that make sense? And this one we're not going to prove. We're just going to state it. And it says the prime divisors of n. If n is a composite number, then there is any prime p, if the p divides n, and p is less than or equal to the square root of n, so that p squared is less than or equal to n. And so the prime divisors of n must be less than or equal to the square root of n. And so we're going to use this to help us determine if a number is prime. But before we do that, it would be helpful if we could make a list of, let's say, all of the prime numbers less than 100. And there's a useful way of making that list. And it's something that's called using the sieve of Aristophanes. And so initially I was going to just use this sieve of Aristophanes, and we'll go back and fill this in a minute. But activity 4.3 is another version of the sieve of Aristophanes that I think is a little bit more fun because it asks you to use colors. Do you folks have any crayons or colored pencils nearby? Do you folks have your activity manuals nearby? Can I switch gears to this activity? Everybody all right? It says Aristophanes was a Greek mathematician who invented the sieve method for finding primes over 2,200 years ago. This activity explores a variation on Aristophanes' sieve. Activity 1, we decided that 1 was neither prime nor composite, so we're going to put an X through 1. It's neither. The first prime number is 2. So we want to color the diamond in which 2 is located with orange. So I'm going to color in the 2 with orange. I think I overcolored because you can't see the 2 anymore. I'm going to try that again. Then we want to use red to color the upper left corner of the key. So the upper left corner of the key of all of the squares containing multiples of 2. So is 3 a multiple of 2? No, but 4 is. 5 is not. 6 is. 7 is not. 8 is. And how would you describe all of these numbers that we're considering multiples of 2? Can anybody think of a word that describes our multiples of 2?
They're all even.
Yeah. And so for each of the even numbers, we're going to color in that upper corner red. And so since they have are multiples of 2 and they've got a corner colored in, they've fallen through the sieve, meaning that they've fallen out of the list and they would not be considered prime. So what we're doing is we're taking out all of the multiples of 2, saying they're not prime. And I'm sorry, I'm a slow colorer. Are you guys coloring in too, or am I wasting your time by coloring? Ah, that one doesn't get colored. And so the first number that's not colored in was the first multiple of 2 that fell through the sieve was 4. Now what we want to do, the first color that's not colored in is 3. So we want to color the diamond around the 3 orange. Because 3 is now prime. And then we want to color blue the upper right-hand corner of any number that's a multiple of 3. So it'd be 3, and then the next would be 6. Then the next would be 9. 12, 1, 2, 3, 15, 18. What would my next multiple of 3 be? 21, 24, 27. And so these numbers are now falling out of the sieve. Any number that has any corners colored in is no longer prime. And so all of those numbers are not prime. So now, what was the first multiple of 3 that fell through the sieve? Well, let's see. 6 was gone already. And so the first one that was left to fall through was 9. 5 is the next number that's left. Since it's left, it will be prime. And I think they tell us to color in the multiples of 5. Oh my heavens, I don't remember what color. Green. So 5, then it would be 10. I'm sorry, I colored in the wrong corner there. 5's the bottom, right? So 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. And then the next number that's left is 7. So that would be a prime. And then I think they asked us to use yellow to color in that other lower corner with the multiples of 7. So we'd have 14, 21, 28, 35, 42, 49, 56, 63, 70, 77, 84, 91, and 98. And what happens is any of the numbers that are left that don't have anything colored in will still be prime. So 11's prime, 13's prime, 17's prime, 19's prime, 23 doesn't have any color. What's the next number without any color? 29, then 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 89, and 97 would all be primes. And I know that those are all primes because any prime factor would have to be less than the square root of that number. And so we've got all of the primes up to 10. And so each of these wouldn't have any prime factors less than that. And so it's an interesting way of looking at those prime numbers, finding those prime numbers. And if you go through and read the rest of the activities, it talks a little bit about, the relationships between the different multiples. But a less colorful way of looking at that I might ask you to do, not on this upcoming test, but on the future test, the test on chapter 4 and 5, is circle 2 because it's prime, and then just cross out those multiples of 2. And so rather than, it's not quite as elegant as coloring in the corners, but we can cross out any multiple of 2 because we now know that it's not prime. And when we cross it out, it's like it's falling through the sieve. And then the first number that was left was 3. So now I'm going to cross out any multiple of 3 that I didn't cross out already. Because if they're divisible by 3, they won't be prime. And we can do that just by counting over every third number. And then what's left is 5. And so if we count over every fifth number and cross them out, we'll be crossing out the multiples of 5, which therefore would not be prime. Then we'll circle the 7, cross out all the multiples of 7. And we can get those by just counting every 7th number. And then all of the multiples of 11 should be crossed out already. All the multiples of 13, 17, 19, 29, 31. And again, everything that's left in this arrangement would be prime. And so what do you folks think of that sieve of Aristophanes as a way of pulling out the prime numbers by crossing out all of the multiples? Is this something you can do? Everybody okay? So then, now that we've got this list of the prime numbers, I'm going to backtrack a minute and look on the preceding page. We said that prime divisors of a number must be less than or equal to the square root of that number. And so to determine if 439 is prime, the first thing I'm going to do is I'm going to estimate the square root of 439. And so the square root of 439, and I took the liberty of working this out before, is approximately 21. So the only possible prime factors of 439 are less than 21. And so they could be 2, 3, 5, 7, 11, 13, 17, and 19. And so if I take 439 and try to divide it, will 2 go in evenly? No, it's not even. I take 439 and divide it by 3. It won't go in evenly. And likewise, is everybody all right? 439 would not be divisible by 5. Let's see, is 439 divisible by 7? Let's see, 7 into 43, 6. No, doesn't go into 19. That's not going to help. If I take 439, don't think it's going to be divisible by 11. If I take 439, see, is it divisible by 13? 13 times 3 is 39. 13 doesn't go into 49 evenly. Can I divide it by 17? Let's see, 17 times 2 is 34, which gives me 99. And 17 won't go into 99 evenly. And likewise, when I try to divide it by 19, it doesn't. And so since none of these are factors, so 439 is prime. And so when you first think of checking to see if a number that large is prime, I don't know about you, but to me it seems insurmountable. How am I going to tell what numbers go into 439 evenly? There are so many possibilities. But if it's going to have any factors, they have to have prime factors. And by what we just said, we're only going to have to check those prime numbers smaller than its square root for the prime numbers smaller than 21. So is 309 prime? In the same way, if I look at the square root of 309, and again, I won't ask you folks to find the square root of a number like that by hand, that I would give to you if I were looking at a test or quiz. I have to apologize. The light in this room is so bad. If I look at the square root of 309, I get about 17. So I'd have to check, does 309 divide evenly by any of the primes less than 17, which would be 2, 3, 5, 7, 11, 13, 17. And can we divide 309 evenly by 2? No, it's not even. Can we divide 309 evenly by 3? Yes, we can. And so this one, because it goes in, we know that 309 is not prime because 3 is a factor. But that seems a bit much. There's one more thing that I'd like to get through tonight with you, and then we'll call it a night. But I think, well, this is a great way of checking for divisibility by the primes. Have any of you learned tests for divisibility where you can look at a number and determine if some things go into it evenly or not? I'd like to look at those tests for divisibility and then call it a night. And the reason that I'd want to add those tests for divisibility is because I think they'll make your life easier. So tests for divisibility. First one, I think everybody knows. A number is divisible by 2 if what? What type of numbers are divisible by 2? Anybody want to help me out with this one?
If they are even,
If it's even. And we know that it's even if the last digit is divisible by 2. Next test, we'll say that a number is divisible by 4 if the last 2 digits are divisible by 4. So what's that all about? Well, let's say I have a crazy number. Let's say I have something like 5,698,214. I'm going to look at this last 2 digits, 14. Is 14 divisible by 4? Does 4 go into 14 evenly?
no.
No. So this number is not divisible by 4. Instead, if I have a number like 732, I'm just going to look at this last 2 digits. Is 32 divisible by 4? Does 4 go into 32 evenly?
Yes.
Yes. And so since 4 goes into 32, 4 will go into 732. So to tell if a number is divisible by 4, we look at the last 2 digits. To tell if a number is divisible by 8, we say that a number is divisible by 8 if the last 3 digits can be divided by 8. So for example, if I have something like 3,000, 416. I'm going to just say, can I divide 416 by 8? And yes, I can. And so it's divisible by 8. The test for divisibility by 8, you might as well, I guess, start dividing the whole number. But over here, this idea that it's divisible by 4 if the last 2 digits are divisible by 4, that seems like a pretty good shortcut, yes? That we can tell it a big, long number by looking. And the reason that it works is because once we get past there, we're in the hundreds, and we know that 4 goes into your hundreds evenly. Likewise, with the test for 8, we know that 8 goes into 1,000 evenly. And so I don't need to worry about that. How about divisible by 5? Does anybody know how to tell by looking if a number is divisible by 5? Anybody know how to tell if a number can be divided evenly by 5?
The ones place has to be 5 or 0.
Okay, so are you all right if I say it's the last digit? The last digit is 5 or 0. And I think everybody's probably familiar with that. Yes, if it ends with a 0 or a 5, you know it's divisible by 5. Next one is pretty, oh, I apologize, I was skipping one. I forgot about this one. If it's divisible by 10, the last digit is what? A 0. And is that one that's familiar with everybody? If the number in the ones place is a 0, our number is divisible by 10. The next 3 I think are interesting and really useful. Does anybody know how to tell if a number is divisible by 3? What you do is you look at the sum of the digits. The sum of the digits must be divisible by 3. So for example, let's say I have 1,413. The sum of the digits would be 1 plus 4 plus 1 plus 3. And let's see, what does that add to? 5, 6, 7, 8, 9. And since 9 is divisible by 3, we know that 1,413 is divisible by 3. Instead, if I have 23,111, the sum of the digits is 2 plus 3 plus 1 plus 1 plus 1. What does that add to? Anybody?
8.
8. And is that divisible by 3?
No.
No. So this number is not divisible by 3. Isn't that a pretty neat trick? Has anybody seen that one before? Next one, to tell if a number is divisible by 6, it must pass the test for both divisibility by 2, and divisible by 3. And so it has to be even, and the sum of the digits must be divisible by 3. For a second, I'm going to jump back to our colored in sieve. And when I look at the colored in sieve, you see how 6 is divisible by both 2 and 3. Then next, 12, 18, 24. And so our multiples of 6 have to be divisible by both 2 and 3. And so to tell if a number is divisible by 6, it has to be divisible by both. So for example, if I have 114, it's even. And if I have 1 plus 1 plus 4, that gives me 6. That divides evenly by 3. And so putting the two pieces together, I know that 114 can be divided by 6. And the last one we're going to look at is to tell if a number is divisible by 9. And here, the sum of the digits must be divisible by 9. And so, for example, if I have, let's say, 6,471, if I look at the sum of the digits, 6 plus 4 plus 7 plus 1, what is that? 10, 17, 18. 18 is divisible by 9. And so my original number is also divisible by 9. And I don't know about you guys, but when I first learned these tricks, I found they made my life so much easier because it gave me a method. And again, probably because I grew up in the pre-calculator days, it gave me a method of telling whether a number can be divided evenly by another number by just looking at it without having to go through and do the gosh darn long division out each time. And so each of these is supposed to make your life a little bit easier by letting you know whether one number is divisible by another. I have a couple others started on the next page, but honestly, the tests are more effort than they're worth. And I know it's a little bit early, but I kind of feel like we've sort of already covered a lot of ground today. Is everybody all right if we stop here and call it a night?
Yep.
Before we do that, while you folks were working on something, I took a quick look back and we've covered the first 2 sections of the this homework. And so you should be able to handle the problems on page 194 and 203. So after you finish that test, if you want to look at the homework questions on page 194 and 203, not necessarily complete them all, but I know that a couple folks have said that part of the problem they have with the homework is they're not always sure what's being asked. So read the questions over and make sure you understand what's being asked. And if you have any questions on those questions, we can kind of get a head start on clearing them up long before they're due. Before I call it a night, though, I know there are several people who came in. I know I let a lot of people in from the waiting room after class started. So let me just make sure. Did Liam come in? No. Mackenzie? Darlene, I saw you come in. You're here
Yep.
now? Okay.
Yep.
You're definitely not absent today.
No.
Did Matthew come in? Desiree? Dorothea? Celestina?
I'm here.
You're here. All right. You want me to mark you as late, not absent, hon?
Yeah.
Okay. How about Renee? And Catherine? Okay. So, have you guys seen, and I couldn't see your faces when we went over them. Have you seen any of those tests for divisibility before? I'm sure everybody knew divisible by 2, 5, and 10. But I think that divisible by 4 and divisible by 3 and divisible by 6 and 9 are nice shortcuts to have to kind of help you out when you're checking for divisibility. Beyond that, does anybody have questions about anything that we did? I apologize, I didn't ask you to bring your activity manuals and crayons. I think if you did, if you had them with you, it would have made that second activity a little bit more fun to do. Everybody likes to color, right? But the sloppy copy that just circle a prime number and then cross out its multiples, does that make sense as a way of finding out all your prime numbers? In this chapter, we're looking at divisibility and primes and composites. So any questions on anything? No? I just picked up my phone for a second and looked at it. And I got a comment from my brother that the bills were ugly. So I think it was a good thing that we didn't have, instead of watching the bills say, hopefully math is less depressing than watching the bills lose.
Well, I had to mute my screen because my man's downstairs freaking out.
Ah, okay, all right. I'm married to a Giants fan. He came from the other side of the state, but he'll commiserate with me. He told me he'd text me when the Bills scored, and I didn't hear from him, so I was getting worried, but. All right, well, have a good day. If you have any questions on those homeworks, please, please, please email me or come to my office hour, or as long as I don't have family commitments, I'm more than willing to meet with you outside of the office hours to go over problems with you. And also that test, make sure you get it done before the 26th. I hope that all the questions are straightforward. If you're taking it and you don't know what's being asked, shoot me. Oh, geez, do I want to do this? Do I want to give you guys my phone number so that you can call me and get a hold of me quickly if you're taking the test and there's something you don't understand? Or do you want to just shoot me an email?
I think the email is better. I don't really think, I think you should have your own private time.
Okay, all right. The test's timed and you only have 75 minutes to get those things straightened out. But send me an email and I promise. Go ahead.
So some of this stuff takes me a while to figure out, and with the last test, I know that some of them had multiple parts, and towards the end I was kind of rushing. So what if we don't finish in time?
I don't think it kicks you out. I think it just says that it's late.
Okay.
That it says that you took extra time. I don't think it kicks you out. And if you take extra time, there would be a slight penalty. I actually looked through it and I shortened the test up. Initially, I was going to give you more time and more questions, but I do think that 13 questions in an hour 15 is reasonable. It leaves you, more than 5 minutes a question. And don't worry about submitting the pictures or anything like that until after the test is done. And again, get your pencil and paper work started if you feel like you're running out of time. Once the test is finished, finish it pencil and paper and send me the picture. Okay?
Okay.
When the COVID first hit in the spring and we went virtual, I kind of didn't time tests. And what happened was some people took days and cheated like anything because taking days gave them time to look everything up. And I realized that is not a fair assessment of what they can do. And so that's when I went to the Blackboard tests that were timed. All right. So anything else? Yes, something else. You have to promise me you're going to have a good mathematical week. Okay? Promise?
I'll try.
All right. We'll see you folks. Bye-bye.
Bye. Thank you.
Thank you for being here. Thanks a lot.
I
Nice.
emailed you my accommodation letter. Did you get that?
Christian, when did you email that to me?
The week before we came back.
The beginning of the semester?
At the beginning of the semester.
I have, let me double check, pardon me. I went through and I looked at all of the letters that I had gotten and made a master list. And it's around here somewhere. This is the third time today that I can't put my hands on my list. I will make note of that fact now. How much time do you get? Like 1.5 times?
I get double the time.
Okay, yes. I remember that, Christian, and I do believe that I gave you double the time on the first test. Okay?
All right.
All right. Have a good one.
You too.
Okay, bye-bye.